Hello, allow me to continue. Last time I left you with a paper which described how cooling is done in a rack, and it was early mobile telephone rack. It is slightly different from the cell phone thing, because when Jensen made that paper in 1972, probably the so called radio telephone was a little not as ubiquitous as now. So, that was from there. Since then things have come a long way, and as I have told you about earlier, the academic lot of analysis is there, most of them, no, tremendous amount of analysis. And in the case of the what do you call our actual industry practices have hired professionals who have had this experience. I will not call it academic or not, and a lot of it has not been freely available in the public domain. So, it is worthwhile reading the public domain material that is available first hand. If I read it and repeat it again, I may have a little bias, so I am avoiding it, and kindly follow. This is from a company called Engineered Airflow. So, one of the first thing is saying thermal, you also start at the device level. So, we have this what are called thermal vias. What a thermal via does is, it from top to bottom they have they put copper which allows us to conduct. So, we have this very interesting thing, no, saying first of all, natural or forced convection, you decide on it. Secondly, you also decide on required amount of airflow. As I have told you in one of my earlier lectures, it is not as simple as saying you give this necessary thing, because it is not like an experimental setup. In an experimental setup, you will be able to pick things and decide what to do. In this case, even if you see a simple what you call a stacked rack like this, you notice that there is lot of shadowing from various things. It may be a loosely talked thing about saying whether it blocks airflow, which happens all the time. So, you have here at this extreme left, you have several what do you call, you have seen this, no, very large components, and then you have certain capacitors, and then I do not know whether these are relays or heat conducting, heat generating components and so on. All these impede effective heat transfer, which will come to a very important issue, that is about optimizing the layout. It looks like even before you attempt any analysis, a preliminary layout is needed, and sometimes it finds counterintuitive. If you put the hottest components at the beginning of the airflow, well, the cold air enters, it looks that they get the maximum what you call advantage, but the disadvantage is that the air in the trailing path is likely to be heated up. Now, that may be exceeding the inlet requirements for the next component in one way. It is a little intuitive and then counterintuitive also. Then how do we deal with it? That is where your what you call design thinking comes in, saying try various alternatives. I have given you an example earlier saying we had a rack of so many, I think total 6 sub racks, and then the only thing we could do is allow inlet air after the third sub rack and then try to exhaust the air that is already pre warmed up, and we have taken it and it works like that. If you see here, locate hotter components in favorable areas, that is what I was just now talking about. Second is heat sinks, saying where all would you put them. And finally, important thing we are coming to here is you need to locate sensors to see how well things work. This you would have noticed happens in already what they call highly optimized, the or ubiquitous PC. So, you notice that the chip itself probably has a way of measuring its temperature itself, and then that is given to a fan, and the fan can run at 2 speeds. And why not the higher speed all the time? One nuisance is the noise. The noise is so ridiculous that you can't afford to keep the fan running at all the speeds. So, you can, I will now see, yeah, airflow commonly used, provided by fans and forced cooling or by buoyancy effects natural. Amount of fluid developed in equipment depends upon the pressure losses. This seems to be most difficult to estimate. It is easy, you have a box and then you have a inlet and you have an outlet, and then the just like you would do in any other fluid control, you have some idea of the system resistance. But in our case, we also have lot of blockages because of the component. So, loosely we can estimate what is the total of area. If you have a cross sectional area, imagine you have this much of a cross sectional area, and then we can, so if I put it like this, if I have this much of a cross sectional area, we have various components and all that, you can estimate now what is the free area that is required compared to the fan inlet, and then you have this free area and then it goes out. Easy to understand, and just like you would do in plumbing, you can also have certain estimates about length of the path length also is an estimate. In the case of plumbing, you will notice that the requirement of the pump, the water pump determines on 2 things. One is the head that is required, another is the length of pipe. So, you this much length of pipe and you know how much of resistance it gives per running meter. Easy enough, is it not? And then next is several places you have features like elbows, walls and all that, where invariably you have a small discharge coefficient. So, if you add all these discharge coefficients and if you add all the pressure drop across the length, and your requirements of how much of fluid you want on the other side, it is possible for you to estimate the size of the pump. It is a little like that, which is absolutely no problem. The place where I have taken this from, obviously they use both. Okay. So, we have about 5 to 8 meters per second in computers, and then in this case they have 1.5 to 2.5 meters in telecom. Natural convection comes to typically 0.1 to only 0.25 meters per second. Is it good or bad? It is for us to decide. My choice is, if there is a way of your managing with natural convection, design everything with natural convection, but give a little bit of aid using have loose fans, or you have a little bit of assisted circulation and so on. Then you have the mainframe computers. Mainframe computers, obviously you have noticed very high, 8 meters per second and all that. It's a lot of, sorry. a lot of blast. So, if you remember in one of the earlier slides which I have shown from Schonolzer, saying it looks like beyond this area 5, actually they have given 6, the rate at which things come down what do you call, varies drastically. So, obviously somebody has done the actual measurement. Previous slide talks to you about sensors. Related to sensors is how do you now take those sensors and use other preventive action, saying can you make the whole circuit design go little cooler. So, we have here, so airflow, air intake and exhaust, air mover, fan controller, fan assembly. You have seen this, no? Air intake and exhaust, it looks very simple, it looks very simple. You pick the air from the bottom and then blow it on top, okay, or you take it at various stages. If you remember, I have remarked to you earlier saying, you see here very conveniently, you can see you have these 4 openings here at the bottom. You see the blue colored thing? There is the opening, you are trying to take it out, and then at the top they have made some way of what do you call, exhausting things. So, anything which you keep close to the ground and whether you like it or not, there is dust. So, it also acts like a very good vacuum cleaner, and the more the velocity is, or even if a low velocity, the more the pressure buildup is, chances are these things will start picking up dust from outside. So, where do you take the intake and where do you exhaust it? Do you directly send it out? It looks quite nice if you can somehow exhaust it directly on top, but you still have the problem of dripping water and things falling from the top. If condensation and all takes place, obviously a smooth channel is not easy to establish. So, invariably you end up with having to exhaust them on the sides or at the back. In the case this is probably the rear of the equipment. They are taking all the air and then blowing it at the rear of the equipment. So, obviously location of air intake and exhaust is critical. Then we come to the actual device which moves the air. Loosely we call it a fan. So, you have axial, you have tubular, tubaxial, then you have externally mounted fans with air filtering, and something which comes here is filter selection. So, you would have seen often one of the things that seem to happen is filters get clogged. So, is there a way of having a filter which, two things, first of all it should not give a pressure drop straight away. At the time of design itself pressure drop should not, and then over the time it should not increase in pressure as it selects. So, we are all, since we are all automobile we have got used to a little bit of automobile, all of you I am sure have come across the air filter inside your car or your motorbike. So, first thing you will suspect is probably the air filter, take it out and dust it off, or better still you can probably pressure clean it and so on. But filters are now about as as sophisticated as anybody else. So, one of them is you have a cascaded filter. From my point from the right side, let us say that the air is coming in and here it is exhausting itself. A cascading filter typically has something which is a coarse filter on the air inlet side, and in between the body of the filter is there, and the last is the fine filter. So, what they do is one or two of them, usually the coarse filter can easily be dusted off, and maybe depending on the construction of the body main filter, that also can be probably you can disassemble and dust it off. Last fine filter is usually discarded. So, this is typically cassette filters which specialty companies do, but all this leads to tremendous pressure drop. So, next best thing is, can we take that inlet or something, have a bellows like thing, but made of some material which is loosely spaced, but can be coated with a gummy liquid. Typically So, there are filters which have a corrugated construction made of a mesh, and then they will give you a spray, probably it is a little viscous what you call oil like thing, and then you spray it evenly, let it rest such that it does not do, and then when you put it back into the equipment, as the air comes, all the dust gets trapped there. Now comes the important part. If you have a sensor, two sensors are required. One is pressure drop sensor. So, on the exit point, if you put a sensor which shows you the pressure, it know that lot of pressure is lost. Secondly, ultimate thing is, if you have somewhere here, imagine somewhere here you have a hot air sensor, a temperature sensor. So, the moment temperature is getting more, you know that more heat is being generated or airflow is not sufficient. And if you have a flow sensor here, somewhere here, the flow sensor can directly tell you two things. If you have a pressure sensor, it will tell you whether the pressure is low. Another is, if you have a flow sensor, it will tell you whether the flow is low. So, large racks and where you can afford to have this, all of these things are used together. So, you have a vane switch, then you have a standard pressure sensor, and then here you have a temperature sensor. Usually something called a Curie switch is there. There is a Curie point, what you call, I am sorry, there is a magnet where the Curie point is adjusted in a critical thing. If something exceeds around 80 degrees centigrade, automatically it changes state, it loses its magnetic field. So, that whole thing is probably put on a reed. You have seen the glass reeds. Beyond a certain temperature, that reed either opens or closes, and then that is an indication that there is something wrong in it. So, usually little bit of time is given and then you can do it. So, this is where you have this something very critical thing called the fan controller design. As I have mentioned to you earlier, you cannot afford to have a fan which keeps blowing a lot of air continuously. So, two problems, it will pick dust. Second thing is fans are noisy, absolutely noisy. While in isolation, if you keep something in a place, in a test chamber, preferably an anechoic chamber, you cannot even hear the sound. But the moment you keep several of them and keep them in a narrow area, and then you expect people to work there, you will notice that it becomes very, very, very loud. Then related to fan controller is the fan assembly, saying how do you make the fan assembly. Different types of fans and so on are there. Seen this here, this word, I do not know if I have shown you already. So, you have all this stuff, card guide structures, circuit base in a rack, fan assembly design, all this typically. Again, I would like to acknowledge that the whole thing is made by Degree Controls, and it is their copyright in 2004. And since this is a educational purpose, I suggest you try to retrieve it again or get in touch with them in case you need any more special assistance. Their application engineers will probably help you. Since I do not get these examples easily in the public domain from the published sources, I am trying to use it. Next we come to equally important thing. Have you noticed it? Very rarely we find such things. Room level. See, very, very critical thing is, it is not just about cooling a printed circuit board by attaching something to the die. Finally, it ends up at how do you cool the whole room. So, we have here saying various type of hot air, cold air system, saying somewhere in the room itself you have input. Air means somewhere you can walk around, other is hot air is the where the thing takes off. So, it is a little like the manifold you have, except in the case of the manifold is fully closed and the variable cross section you can control. In the case of an AL, it is an axis where people need to probably walk around, and then so we have all these various what you call things very neatly mounted here. and we have airflow distribution to the cold airs, floor layout per heat rack dissipation. So, heat rack what I call heat dissipation, floor layout itself, how do you space them, and wherever you have communication equipment and such equipment, amount of cabling and wiring is very high. You cannot imagine how big it is. If I get a chance, I will try to take a picture from our own. We are a very small place. We do not have many computers, but in spite of it, if you got, I suggest you go and have a look or just check up on the now the Bible, the internet Bible, and you will see that they are very dense. So, we have here things which are inlet into thing, and then you see here this is from a data center. Data centers obviously lot of stuff is there. Then you have airflow balancing through the room. Kindly what you call permit me to take a stupid take on these things, while our interest is to keep the all this racks and all, I mean the peak temperature of the devices in a reasonable control. Generally our tendency is to stick a few indoor units, so called split tire ACs. Call the what do you call the person who installed this thing, and then he has his own estimate. He will say, sir, you probably require 8 tons what do you call cooling air conditioning unit, and even the tonnage they specify has a little problem. So, take all the bring that fellow, and then most important we end up is, because it is a more like a firefighting, no, we end up sticking the evaporator blowers in a convenient place in the wall, because the plumbing for the the what do you call refrigerant plumbing also is important. And our bad luck is those units chill the operators, people are supposed to do, and then independent of those coolers, the equipment continues to get hot, and then obviously nobody wants to be like that girl who freezes, or some of the Christmas stories. First thing they do is play with the thermostat and raise the temperature. The moment you have it, the whole thing goes. So, here critical thing is how do you balance the airflow. Whatever that small louvers they give in the indoor units may or may not be sufficient. So, it may be more appropriate for you to put small. There are fans which probably are about 200 to 250 mm diameter, multi-directional. You put them somewhere and ensure that airflow is balanced throughout the room, and placement of the AC units. So, it is not very easy. Then we come to recirculation of the hot air. If the air becomes hot, what to do with the hot air? In a very cold environment, probably it makes sense. In a hot environment like us, what do we do with it? Do we exhaust the hot air? Then when the inlet air comes from outside, you still have problem about it. Then you have another important thing is how efficient is your whole cooling system. I am talking from the electronic systems engineering department. So, obviously we take a systems approach, saying attempt a top down approach. Then something very related is to equipment reliability. One of the reliability of this whole equipment. Second thing is what happens to the reliability of all the cooling equipment. So, I will not call it a what I call trial and error or hit and miss. You need to just consider it. Nothing, I mean nothing great about it, but considering is more important. So, we come to important thing, saying understanding fans and system architecture. So, next two slides, 2 or 3 slides are quite important. You will notice that I will try to go a little forward, try to see if I can get the fan model. Yeah, I will go back again to where we have started. This is simple tube axial fans. So, you will see that early on in one of the lectures I mentioned to you saying there are these what you call fans where they mention the static pressure, saying typically it will give you about 1 inch, meaning when no flow is there it gives about 1 inch, and they also mention a delivery, saying it gives 100 CFM, 200 CFM and all that. Main attraction is they are inexpensive. So, you can have a full wall, just like you have a video wall, you can have a fan wall in which let us say every tile which is spaced say about 600, 700 millimeters, 600 above approximately, all our what do you call false ceiling tiles are all those 600 mm and all that, no. Somewhere in the middle maybe you can have all this. There are, if you see your cabinets, your 19-inch racks and cabinets inside, you have those 400 mm by 400 mm trays in which fans can be fixed. Have some of these things distributed freely wherever you want. It is not very costly, and depending on your type of operation, you can have them working off 230 volts or with a controlled input. If you have a 12 volt input, you can externally control the fan speed by reducing the voltage. But main issue is pressure capabilities are limited in high impedance systems. See here, if you read the what I call extreme right of my curve, very drastically the flow comes down, extremely drastically it comes down. The slightest this thing, even if you put those normal heat sinks, forget about space between the thing, we have a little problem. When they talk about low impedance, it means free flowing. If generally things are free flowing, it is very easy. I mean, it is a stupid way of saying, stick a few things down, but the thing is you can attach a few of these things on the bottom of the rack and then they manage it, no problem. So, it is ideal for low impedance. Cap pulses are seriously limited in the case of high impedance systems. Next slide talks about different other types of things compared to an axial fan and all that, and then actually how does an airflow system work here.